Let's talk about how to make Bode plots. So Bode plots were originated back in the days before they had computers and were used as a way to make a graphical representation of frequency response and make a plot, a graph that would allow you to see what the frequency response of a transfer function or something looked like. These days, of course, we do have computers, and so we can make plots of the magnitude and phase of a frequency response without any trouble, but Bode plots stay on because they allow us to understand and break down into pieces and see what's really going on in a frequency response. Before I really get to talking about it, I probably should talk about the decibel. So we're going to be representing things. A Bode plot's a log-log plot. We're going to go log in frequency, and we're going to go logarithmic in the vertical axis as well. So way back in the day, the bell was, after Alexander Graham Bell, was defined as the base 10 log of the ratio of two powers, okay? And because those numbers aren't as convenient as we might like, we might do the decibel, or dB, which is 1/10 of that, so it takes 10 times as many to get the same number of dB. So we multiply times 10 times the log of the power ratio. In many cases, we're going to talk about not power ratios, but voltage ratios. And the voltage in the second circuit will be over some, or the voltage, or the power will be proportional to the square of the voltage. And so we'll get that. And so this is still the definition, so 10 times the log, but this can be rewritten as the ratio of two voltages squared, and based on the properties of logs, then this becomes 20, so we just multiply by 2. And so either of these definitions is correct, and the handy thing about this is once you've got it in dB notation, there's no ambiguity. So whether you're talking about voltage or current doesn't matter once it's been put into dB. You just have to know which formula to use. And current ratios could have been the same because the powers are proportional to the squares of the voltage or squares of the current. Okay, and you know, when you're in a particular field, we're in engineering here, and there are certain kind of numbers that everybody should know. You know, it's interesting, if you're a carpenter and you live in the United States, and somebody says, what's the decimal equivalent of 7/8? You probably know that, even though I may have to scratch my head. But carpenters know those things. That's just the sort of stuff you know. What is it, 0.875? But not everybody would know that. They're just certain things that you just understand. Well, here's a few of them that we're going to need as we go along. If the ratio is 1, is unity, so that's 0 dB. So 20 times the log, or 10 times the log of 1 is 0. All right, so that's very important. So when we talk about unity gain or gain of 1, we mean 0 dB. From the most basic properties of logarithms, if we're talking about 20 times the base 10 log of a voltage ratio, where that ratio is 10, then the properties of logs, of course, this is 1 and this is 20 dB. So 20 dB is synonymous with 10 times the voltage. All right? That's really important to just know that. If we have a ratio and it's the other way, if it's 20 times the log of 1/10, then that corresponds to minus 20 dB. So negative dB correspond to ratios less than 1, positive dBs for ratios greater than 1. Let's do a couple more. This one is more subtle, and you need to know more. It turns out that the base 10 log of 2 is about 0.3, and that 20 times that is about 6. So a 2-to-1 ratio is about 6 dB. This is approximate, but it's a good approximation. I think it's 6.02 is the actual ratio. So 20 times the log of a half, a voltage ratio of a half is minus 6 dB. All right? If you know anything about logs, you can go and do a bunch more of these. I'm not going to do tons of them, but 20 times the log, the dB thing for 4 is just 2 squared, which is twice that. That's 12 dB. And so you can keep doing these things. If I did, I could do lots and lots of those and derive a whole bunch of correspondences to these numbers and get sort of round number, good approximations for these things. Another one that we might need is that 10 times the log, so if we have 10 times the log of a power ratio, which is 2, it's going to be the square, that's 20 times the log of the square root of 2, and that one's 3 dB, which is half of that. Okay? So all of these things we're going to use in our discussions today. I got something else I got to tell you before we really get started. When we do Bode plots, and we want to look at the frequency change along the frequency axis, all right, so we're going to be making plots of omega on the log scale. We're also making plots of log of omega. We're going to use ratios are going to be the two things that count. So if this is omega naught, corresponds to this point, and this one is 10 times omega naught, then 1/10 omega naught will be over here, and the spacing from here to here is equal to the spacing from there to there. A ratio in frequency of 10 to 1 is called a decade. 1 decade. Here's another decade. All right? And so you could say that the ratio of 10 times omega naught to 0.1 is 2 decades. All right? Another one is more subtle. This one's fairly obvious, but this one is not so obvious. If on some other scale I have omega naught is here, and this frequency is 2 omega naught, then the same distance would get me to 4 omega naught, and the same distance would get me to 8 omega naught. Each one of these factors of 2 in frequency is called an octave. An octave. If you know anything or ever took Latin or something, you know octave has something to do with 8. So what in the world is that doing in here? That's very confusing, I realize. It actually comes from music theory. If you go do, re, mi, fa, sol, la, ti, do, that's 8 notes. And from do back up to the note that you call do again, that's twice the frequency in music terms. So twice the frequency is a ratio of 2 in frequency, which is called an octave. And again, that's called that because of musical notation. So you never know what you're going to learn around here. So we'll come back to all of those things, but this is actually stuff you need to know. And who knows, maybe I'll come back one of these days and make a video and we'll talk about all the different numbers that you can get, 3 dB, 6 dB, minus 8 dB, 9 dB, 1 dB. A lot of those things you can work your way through and make a little table that'll tell you, given some number, how many dB is that ratio, and not have to really memorize much because you can re-derive it very quickly. But maybe we'll do that another time. All right, backwards to Bode plots. So again, Bode plots are plots of the magnitude of magnitude and phase of frequency responses. What do I mean by frequency responses? We've elsewhere talked about the fact that if we want to know the response of a system, a lot of times we can represent this in terms of the characteristic polynomials. So maybe we would have a polynomial of the form b sub n s to the n plus b to the n minus 1, s to the n minus 1, etc., all the way down to maybe b0, a constant term. And in the numerator, we might have a to the mth power, m minus 1, s to the m minus 1, this is a little tedious, all the way down to, for example, a0 constant term, and maybe there's another constant out front. So we can typically express our transfer functions as ratios of polynomials in S. Now, again, we could talk about the possibilities. We've got several different kinds of frequency responses we do. One of them is transfer functions. You put an input in someplace in the system, you get an output somewhere else. That's a transfer function, from here to there, transfer, okay? There's some rules about the orders of the numerator and denominator in transfer functions. I don't know that we need to go through them, but we may mention some of them. Another possibility is you apply, for example, a voltage at a place, and then you measure the current that happens at that case, or vice versa. In those cases, we can talk about the admittance or the impedance of those things. There's a different set of rules for these things. And another possibility is transfer functions where we would put in a current and get an output of a voltage and vice versa. So there's questions about the order of these things. There's rules about m versus n, and there's orders about the lowest non-zero coefficients of these two. And maybe we'll talk about them elsewhere. So what in the world does this thing happen? I'll show you some ways that we can estimate the A's and B's in some circuits, but this is a big mess. I've shown you ways that in some circumstances I may be able to factor this thing into simpler forms, and that's what we need for Bode plots. So being able to factor this would be nice. So typically the functions that we're going to do may have a k out front, but they're going to be of the form s plus, and let me see if I have a in my notes. Yeah, we'll call it omega p1 s plus omega p2 times, and we maybe have s plus omega p sub n. We'd have n roots for an nth order polynomial. And then we might have s plus omega z1, s plus omega z2, etc. And again, depending on m and the other things, this would be s plus omega z m. And the z, or the p's, have to do with the fact that the roots of this thing, the value of s that would satisfy this polynomial, I'm assuming these two are equal, the value of s that would satisfy that in this example would be s equals minus p1. If s is equal to minus p1, it's a root of the denominator. A root of the denominator is called the pole, and the pole frequency would be omega p1. In the most interesting functions that we're going to look at, the values of all the s's that would satisfy, that would be poles, would have negative real parts. And we'll talk about that more at other times. So I'm going to start out by assuming that the poles are all real, negative real numbers. There's a bunch more relationships that we can talk about. Usually for many things the b's will all be positive real numbers, for example, but some of this doesn't depend on that. So this would be the pole frequency. So a pole is a root of the denominator. Correspondingly, the zeros are roots of the numerator. All right? So roots of the upper polynomial would be things like s sub 0, 1. The first 0 would be minus omega z1. So that's the pole. So it's just the z. These things all have units, in most cases, of frequency. And so the roots of the values of s that make the polynomial go to 0 are called the zeros for reasons that may be obvious just by inspection. All right. So to do Bode plots, the first thing I'm going to show you is how to factor this thing, assuming that all these roots are real. Now, it's also possible that we could have factors in the middle of this whole thing that are of the form s squared plus, I don't know, 1 over q times s omega 1 plus omega 2 squared or something like that. We could have factors in the second order polynomials here. And we'll come back and do some of those later. We've seen that that's a possibility. As you know, for polynomials with real coefficients, I guess, the roots are always either real or complex conjugate. And those are all the cases we're going to do. All right? There are a few other restrictions that we may talk about before we're done. Again, the real parts of the roots of the denominator are always in the left half plane. In the numerator, not necessarily the case for the functions that we'll be looking at. All right, so what I'm going to try and do is just do this by some examples of typical transfer functions. The trick is then I'm going to assume that we have simple polynomials. We won't have them quite as complicated as this, or in other words, we're going to have smaller m's and n's, and we'll just do easy ones. And the trick is we're going to do a magnitude plot, which is a magnitude Bode plot, which is going to have BODE, and it's going to be a log-log plot. We'll also do a phase plot of the phase of a transfer function as a function of frequency, where s equals j omega, and we're going to let s equals j omega and make the phase as a function of log frequency. All right, and those two together will be the full Bode plot. All right, so how do we do these things? We're going to have a function of this form, and we're going to evaluate for s equals j omega, and I'll tell you the rest of the story as we go along. All right, Let's do it by example. Let's do some real easy stuff. Suppose we have a transfer function for starters that is just, let's call our transfer function h of s, and suppose our transfer function is h of s equals s plus alpha, just to make something up, where alpha is a positive real number. Then the magnitude of h of s, where s equals j omega, is just j omega plus alpha, where omega is a real number and alpha is a real number. Alpha is a real positive number, okay? The magnitude of that is what we're after, and I hope you remember that the way you find the magnitude of a complex number is we take the square root of the sum of the squares of the imaginary part and the real part. Okay, so that's still fairly complicated. The trick with Bode plots is we're going to make two asymptotes. We're not going to actually evaluate this because we're trying to simplify. The simplification is we're going to break this into two regions. We're going to have a region where omega, the frequency that we're evaluating at, is much less than alpha, and get what happens there. And then we're going to have another approximation where omega is much, much greater than alpha. Well, when omega is much, much less than alpha, you can just start with the original function here. When j omega, magnitude of j omega is much less than alpha, at the low frequencies, this thing is approximately omega. So this is magnitude of h of j omega. And when omega is much, much less than alpha, this thing is approximately equal to alpha, a constant, independent of frequency. All right? So magnitude of h is equal to alpha, a constant. When omega is much, much larger, then we can go out and look. This s term is the one that's bigger, and this thing is approximately equal to s. H is proportional to omega. So we've got two asymptotes, and they're both proportionalities. And so if we have this is a function with a single zero, and we can make a plot. And the trick is, if we can find a flat part in the gain, which we have here, we evaluate this. And this is, well, I'm not going to always write this, but this is the dB form of, I'm assuming this thing is a voltage ratio, so we use the 20 log of alpha, and that is the constant value, and this is our approximation on our log frequency axis, and the vertical axis is going to be in dB. All right, so we're going to put magnitude of h of j omega in dB, and that'll take care of all the log things. All right, and we're assuming h is a voltage ratio, which is why we're using the 20 form. All right, when we get out to here, this thing is going to be proportional to omega. And the last thing to keep in mind is that these two things are equal when omega is equal to alpha. They make equal contributions. And that is the point at which our two asymptotes will cross. So proportional to frequency on a log scale looks like this. Now, for every 10 times increase, which is 1 decade, we're going to get a 10 times increase in the dB, which is 20 dB. So this slope is 20 decibels for every 10x increase in frequency. We say this is 20 dB per decade slope plus 20 dB per decade slope. All right? And this is the asymptote of this curve. If we just project this to where they meet, this is where the frequency omega is equal to alpha, where alpha is the frequency, sometimes called the cutoff frequency or something like that. And so we had the alpha expressed in dB, and we had that asymptote. We take this thing and we just start here and we work our way up. We increase the slope by 20 dB per decade. And that is an estimate. Now later on we'll come back if we want to put more stuff in there, and you can see that when these two things are equal, that this will be the square root of 2, which we said was a 3 dB error. So at the frequency here, when we're in between these two things at the middle, we make an error in this case of 3 dB. And so the actual plot, if we get on a computer, is 3 dB higher than where our intercept would be. So it's whatever this is in dB plus 3 decibels, that's the value that it actually goes through. So the rule that we'll say is when we have a single zero, it causes the slope to increase. If you started from the top, it's coming down like this, and then it flattens out. So the slope increases by 20 dB per decade every time we pass through, if you will, the zero. All right? The second example I'll do is a pole. We plot it on the same axis, and this is going to be a little simpler, so we'll have some k in the numerator, s plus alpha in the denominator. If s equals minus alpha, this thing goes to infinity, so the pole is at s equals minus alpha. The magnitude of this thing is just 1 over what we just had, so we could keep going through all of this. 1 over alpha, k over alpha, k over alpha, k times omega at all these things, or k over omega at all these things. So let's just look again. So the magnitude of this guy is k over, s equals j omega. That omega is the imaginary part, the real part. So this is my function for this. But we're not going to use it directly. We're going to say when omega is much greater than, much less than alpha, the s goes away. I just put my hand over it and I can see the remaining function, and I get that the magnitude goes as k over alpha, whatever that is. So I'm going to make a plot, my Bode plot. We'll start, again, this is magnitude of h in dB versus log frequency. And this value will be 20 log of k over alpha. I'll just put k over alpha expressed in dB. And when we get to some frequency, which the frequency is alpha, that will be equal, after which this thing will now go inversely proportional to frequency. The terms involving alpha go away because alpha is small, and s equals j omega, we're going to get k over s, which is proportional to k over omega. The slope for that on a log plot is minus 20 decibels every time we increase by a factor of 10, or minus 20 dB per decade. And that's how this thing was plotted. Again, if we evaluate this at s equals j omega, s equals j alpha, then this thing will be k over the square root of 2. And on this plot, it'll miss by 3 dB. So this is the minus 3 dB frequency below that. By the way, 1 over the square root of 2 is about 1 over 1.4, which is about 0.707. So on a linear scale, 3 dB minus 3 dB is about 0.7. All right, 70%. Sometimes called a half power point. Okay, so that's the general thing, and everything we're going to do with real poles is made up of combinations of all that good stuff. Let's do some more examples, and we'll be there pretty soon with good understanding of everything we need here. So let's see, what is the best way to do this? Let's do one with 1 pole and 1 zero. Let's suppose we had a transfer function that was, my h of s was, let me make up some numbers here, s plus 1 divided by s plus 10. And let me just put a 10 out front. We'll put some numbers in this thing. Now, what 1 and 10 are, they're frequencies. And when I was doing this thing, I was thinking of them as frequencies. So I would say this has units of, say, kiloradians per second, just to make up something. Maybe this is 10 kiloradians per second. Kiloradians per second. Remember that omega in radians per second is 2 pi over the period, 2 pi times the frequency in hertz. Okay, so we got this extra 2 pi to worry about. But anyway, that's just a reminder. And this 10 out front is just because I decided to put it there, just to make it an interesting problem. And these could have been radians per second or any other units you wanted, as long as you're consistent and express s in the same units, if you will. Okay, so here's the deal. The thing I haven't talked to you about is the first thing you want to do is see if you can look at the function and figure out, is there a place at which the gain is independent of frequency? If s is really small, much less than 10 hertz and also much less than 1 hertz, so if the frequency is much less than this zero frequency, then the s's will cancel out, and the gain of this thing is magnitude of h is 10 times 1 over 10. At sufficiently low frequencies at a good approximation, that'll be 1, and that's going to be 0 decibels. All right? So for this thing, the first thing I'm going to do, I should just keep these axes on there, but I haven't. So here we go. So this is 0 dB. Magnitude of this H is 0 dB at low frequencies. And it's going to stay there until we encounter the smallest of these two things, which is at 1. So my plot is going to go unity on that. And eventually, when we get to S equals 1, it's going to encounter a 0. The 0 means that it breaks up. And so this slope, this asymptote, goes up at plus 20 dB per decade. All right, plus 20 dB per decade. That means proportional to frequency, by the way. dB per decade. All right? And it's going to stay on that trajectory, or close to that asymptote, until it gets to a new frequency at which, at S equals, or omega equals 10 units, at which case the gain is going to break down because it's a pole, and it's going to flatten back out again. Okay? And so this is going to be at 1 radian per second, or kiloradian per second, as the case may be, and this is going to be at 10. So if it started at 0 dB and went up by a factor of 10 proportional to frequency, this thing is going to be at 20 dB. And then it's flat again. So our asymptotic plot starts at 1, hits the 0 at 1, okay, and then it hits the pole. So this is 1 and 10. And then it says at sufficiently high frequencies, the omega terms are going to be bigger than 1 and 10. We can get rid of those. These two things will cancel, and at high frequencies, the gain is a constant, which is 10. 10 voltage ratio corresponds to 20 dB, and this says the gain at high frequencies is plus 20 dB. All right? So, in many cases, you can then, with these constant value poles, we can just count the fact that we start at a flat thing, evaluate the function, and then go until we reach the first pole or 0 in either direction. There's other places. This thing was flat at high frequencies. I could have started out here and said at very high values of S, the 1 and the 10 don't matter anymore because they're both smaller than the magnitude of S. These would go away. This thing would evaluate to 10. We could have started out here at high frequencies, worked our way over. The first thing we get as we go down in frequency is to this pole at 10 units, at which point the phase, whenever you encounter a pole, the slope goes down. So it goes down from there until it pulls down, gets to this one, and now we hit the 0. The 0 makes the gain break up as we pass through it and we flatten out. So the breaking up, breaking down thing works in from either point of view, either direction. All right? We just need a few more examples and we'll really be where we want to for we're doing magnitude Bode plots. Let me do a couple of other possibilities just to see what else could happen. Let me make up a transfer function, change this to a transfer function. I was reading online and a lot of people said, no, you can't write them this way. You have to normalize all these poles. I'm going to add another one and I'm going to write it as S divided by 100 plus 1. And some things on the internet said that all of these should have been, that this one should have been S divided by 10 and then it would have changed this number. It's really not that important that you have these written in a particular format. I could rewrite this in different ways. It's just more convenient in some cases. So this is particularly convenient for the way I'm doing it. So if we start down here, S is much smaller than 100, so this term is just 1, so it doesn't matter. So until we get up close to 100 hertz, this thing is not actually going to affect our transfer function. And so far from here over, this transfer function is correctly plotted. As I continue up beyond 10, however, and get closer to 100, this one, which is going to be j omega over 100 plus 1, and at sufficient, when we get up to 100, when omega is 100, these will be equal in magnitude, and then for frequencies greater than 100, we've encountered a second pole. So when we get out here to one more decade, which is the same distance from here to here as it was from here to here, so if if I scale it right, it should be something like this. We're going to get a new asymptote at s equals 100 units. At which point, this is a pole, so it's going to break down again, and now this thing will go with minus 20 dB per decade. So when we started out flat, the lowest frequency we encountered the 0, which made us break up. Then we had the pole that made it flat, and then we had another pole which turned it back around and made it started dropping off with frequency. All right? Think about why that's true and make sure you're comfortable with it. Now I'm going to do a new transfer function. Suppose the new transfer function is this one, except for this thing now is to the second power. So that would have been, maybe it's easier to clear to write this out separately, s over 100 plus 1. That'd be the same thing I just erased. And now when we get to this one, there is two of these effects. And so when we get to that case, with the square, we're going to do twice as much. So when we get to 100, we started out with 0 slope, and now we're going to be proportional to omega over 100 quantity squared, which is actually minus 40 decibels per decade. Okay? So we were flat, and now we add double as much slope. If this thing had been cubed, this thing would have been even steeper, and this slope would have been minus 60 dB per decade. Okay? So these are still real poles, but now we have them in multiple times. All right? So we can do lots of things there. By the way, the errors out here would probably be bigger as we went to higher powers, but we'll come to that later. Okay, there's still one or two little cases that may be problematic here. Let me do at least one more example. Suppose we have a case where there's no flat gain anywhere. That gets to be annoying. You can have a transfer function like s in the numerator. That's the key. So I can have zeros at the origin. S equals 0. We could say s divided by 100 plus 1. This is a plausible transfer function. Now, in this case, actually in this case it's not too bad because we can start up at very high frequencies. At high frequencies, the 1 drops out, and this thing would have a gain of omega divided by omega over 100. We could forget the 1 equals about 100. All right? That equals exactly 100, which is 40 dB. So this plot we could do by starting out at high frequencies at plus 40 decibels, a factor of 100, and then as we go down to 100, we get to a single pole response like that. This would be at s equals 100, or omega equals 100, and this would be plus 20 dB per decade. As we come down from high frequencies, the slope decreases. Now we can see that as we go up from low frequencies, the slope decreases due to the pole. So again, this is not an example yet of one that doesn't have a gain at a particular frequency, but let me find you just one more. Also, okay, I got two more things we can do, and then we'll hopefully we'll have all of this, and then you probably need to do a bunch of practice before you're going to feel confident about all of these. And you may have questions, so you'll have to find somebody to ask. Let's just do this one. I've got a transfer function that says h of s equals 100 times s divided by s plus 100 quantity squared. Now this one actually turns out not to have any flat regions. So that's a bit of a problem, and so we need to figure out what to do about this. This makes it a little more complicated. If I go to very low frequencies, then at s much less than 100, this is s over s squared, which is proportional to 100 over s. So that's not independent of frequency. So I say, okay, how about at real high frequencies? Well, at real high frequencies, did I do it wrong? I think I did it for low frequencies. At low frequencies, s is proportional to frequency. And so at low frequencies, the s drops out. This is just a constant, and this thing is proportional to frequency. At high frequencies, the 100 drops out, and this thing is inversely proportional to frequency. In other words, somehow or another, this thing goes up and comes back down. This is called a bandpass response, and that's what we're going to get. So at this point, there's really nothing you can do except for pick some value of S that's a long way from any poles or zeros, and just plug in S equals some number, and then approximate away. So if I say at S equals 1, or J or whatever, at S equals 1, the magnitude of this H is equal to approximately 100 times 1, and at 1, this thing is divided by 100 squared, and so this thing is equal to 1/100th. So at S equals 1, this thing will be 1/100th, which is minus 40 dB. And we'll start out right here at 1 hertz. One unit, 1 radian per second. All right, S equals 1. And then we see that at very low frequencies, that's much less than 100, so the 100 becomes unimportant. So this thing is now proportional to, it's proportional to frequency. At S, very small, this is just the only frequency-dependent term, so this should be going up at plus 20 dB per decade, proportional to frequency. And it's going to continue on this slope until it hits the pole. At that point, it's going to have 2 breaks down. So it doesn't go flat, it comes back around, and it goes at minus 20 dB per decade, if I can write that. And it continues on its way from there. Now, if this was at 40, and this was at 1, and if this was 100, then according to the asymptotic plot, this thing would have gone two decades up in frequency, and was proportional to frequency, so this thing would have hit 0 dB up there. It would have been minus 20 dB at 10. It should be, again, at 1,000. It should be at 10 or 20 dB, etc. So this is the asymptotic plot. If we go through this carefully, again, we haven't really looked at the approximations we're making, but if you do it real carefully, you'll find that this thing is down by 3 dB for each pole, and that the actual thing will dip below this, and instead of making it up to 0 dB, it'll make it up to minus 6 dB. And the actual plot would look something like that. Okay? I think that covers all the stuff, all the things that you could do for real poles, zeros, all the cases, zeros at the origin, etc. Now, we haven't done the phase. So let's talk about how to do the phase plots for some of these same examples. So if we take the phase plot, there's a whole set of approximations we can make and get, again, linear phase approximations based on simple transfer functions. So let's just consider an h of s equals some constant times s plus alpha. That was the first example we did when we were doing the magnitude response. It turns out that what we now want to do is make a plot of the angle associated with this function when s is replaced by j omega. And it turns out that we need to know something about the inverse tangent function. The phase of a complex number is the inverse tangent of the imaginary part over the real part. Okay? And so in this case, the imaginary part, this thing will become, for s equals j omega, a constant which doesn't matter, times j omega plus alpha. The imaginary part, then, is the inverse tangent of, the imaginary part is omega, and this part is, the real part is alpha. Now, that looks a little intimidating, but it turns out we can make some nice approximations of this thing. You can get your calculator out and do it accurately. This thing has 1 0 on our log scale. It has 1 0 at alpha. And here's how we do the phase plot. For if we say at alpha, it turns out that this thing is going to be 45 degrees, pi over, what is that, pi over 8? 45 degrees, pi over, yeah. Then our approximation is going to be, if we go to 0.1 or 1/10 alpha, then this thing is going to come by with a slope like, whoops, with a positive slope. And at alpha, frequency of alpha, this thing is going to do this. And we make a plot that goes up to 10 alpha and down to minus 1/10 alpha. And this thing will hit 0 degrees down here and plus 90 degrees up here. And that's actually a pretty good approximation to the transfer function. So again, the three frequencies that we care about are the cutoff frequency alpha, alpha divided by 10, and alpha times 10. And we say that it's 45 degrees of phase when these two things are equal. So when these are equal, the inverse tangent of 1 is 45 degrees. And then this thing is a straight line that goes between these two limits. And it hits 0 down here and plus 90 degrees there. If you make an exact plot of this and compare it to this guy, it can be shown that it actually looks about like this, where this error is 5.7 degrees, and this error, so that's minus 5.7 from here to here, and this difference is 5.7 degrees, approximately. So it's a pretty good approximation. It's exact right here at 45 degrees. That's exactly what we get. Okay? If we do the same sort of thing, I'm just going to go over to the other piece of board here. If we do this for a pole, so we have h of s equals k divided by s plus alpha, and we want to know the phase of that, then the angle associated with h of j omega in this case, so you can actually show that in general it is the inverse tangent of the imaginary part of the numerator divided by the real part of the numerator, divided by, nope, not divided by, minus the phase of the denominator. Imaginary part of the denominator divided by the real part of the denominator. So when we go to do this, the real part of the numerator in this example is just a constant, so that's 0 degrees, and it's the phase of this guy in this case is just minus the inverse tangent of these guys. So in other words, the plot of this function, if we evaluate at 0, it's at low frequencies, it's at 0. It stays there until we get to alpha over 10. It goes down and hits minus 45 degrees at a frequency of alpha, and it continues down with that same slope until it hits a frequency of 10 alpha, where it flattens back out, and that happens at minus 90 degrees. Okay? So the pole, again, makes the phase go negative. The 0 makes it go positive. It's 45 degrees at the pole or 0 frequency, and the total swing is 90 degrees per pole. And if you wanted to, you could talk about the slope of this, which is 45 degrees per decade for each 0 or pole. Then, and I'm not going to do too many more examples of these, but if you have multiple zeros and poles, you just add these segments up at each frequency involved. So, for example, this is one that you may see in a tone control for like a sound system. Bass and treble controls have transfer functions that look like s plus omega z divided by s plus omega p, where these are two, in general, different frequencies. We've already done this example in the magnitude response. Depending on which is lower, omega z or omega p, the magnitude response of this might do something like this. If the pole is lower in frequency than omega z, this slope is minus 20 dB per decade. Okay, or you could do, this would be like either a bass boost or a treble cut, or you could have had one that does something like this. That's the same one I just did. So if the 0 comes first, then we'll go up first, and then we'll hit the pole. So what are the corresponding phase plots of this? Well, we need to come down and find out how far these things are separated. So we've got omega p over 10. We've got 10 times omega p. We've got omega z, the 0 frequency, over 10. And we've got omega 0 times 10. Okay? So each of these frequencies is going to cause a break in the slope of the phase plot. So in this example, as we reach to this one, we get to within a decade below the pole. If we start out at 0, so this thing has, if we had a minus sign out front, it would be, let's just do that for fun. If we had a minus sign out front, we would start at 180 degrees. If we have a plus sign, then we'll start at 0. And if you start at minus 180 or plus 180, it usually doesn't make any difference. They're usually the same thing. All right, so when we get up to here, this thing is going to have a segment that's going to start and finish there. And so this is going to be at this frequency, it'll be minus 45 degrees. And at this frequency, it'll be 0. And down here, it will be minus 90 degrees. And then we come up to here, and it starts back up. And it'll reach this one by the time, so at omega 0, we'll be back up to minus 45. So we just add these things. So this is the total phase that we would get, starting at 0, hitting minus 90, working its way back up to minus 45 at omega 0, and then completely flattening out 10 times above the 0 frequency. If these two frequencies here had overlapped, then we would have had, so if we just move the entire thing a little closer to the left here, then all of this thing would shift to the left with it. So if omega p and omega z are a little closer together, then 10 times omega p could be here, this is omega z, and 1/10 omega z could be there, and these two things will then sort of overlap. So we start down with a slope set by the pole. We get to minus 45 at this frequency, but at this frequency we start flattening out. We cancel the decrease in phase with an increase due to the 0. When we get to this thing runs out and it starts back up and completes its response at 10 times omega z, which is over here somewhere. And this thing then never gets all the way down to minus 45. And so if you work at it, you can do the superposition of the two phase plots and figure out how much phase you get down here. And this becomes the approximation to the phase, is a plot that looks something like this. So it starts down and then it comes back up. So that's what the phase would look like. Okay, so you may need to work on those for the phases of more complicated systems. It can be somewhat tedious, but you can use what we've learned to get some idea of what the shapes of these functions are. And if you're careful and follow all the rules and superpose, you can add up the effects of all the magnitude responses in dB, and you can add up the effects of all the phase responses in degrees or whatever, and get estimates of what the overall curves look like. So that's most of what you need to do for the phase plots. Yeah.